I'm telling you, it's not gonna be good.
All right.
Talking about that 540.
Hello and welcome, everyone. We're about to begin the Celestial Theodolite update number 13. Today, we're going to be taking a new look at the data with the spreadsheet that I made. The battle of the spreadsheets has been ongoing for a couple of weeks now, and I figured I would take a gander at the data and make my own spreadsheet. And because I'm not very familiar with this kind of stuff, I have to make it real easy to understand. So hopefully when we go over this, it makes things a little more clear about the purpose and premise of the Celestial Theodolite. And we're going to go over, after we go over the first example here and we understand the spreadsheet and how it derives everything, we will go over we will go over individual mountain peaks and look and compare what the globe predicts and what the flat earth predicts. So remember, this all started with a simple hypothesis versus null hypothesis, assuming that the earth is a globe is our hypothesis, and our null hypothesis is that the earth is not a globe, i.e. it's flat. So two mutually exclusive outcomes. And through this process of using the true positions of the stars with respect to occlusion timings, we're able to externally test an internally consistent system, which is the latitude longitude system that makes up the globe that makes time correspond to positions of stars. So using their own snapshot of a position of a star on the first cusp of Aries with respect to adding 15 degrees per hour to that in perpetuity, we can relate an angle to where a star once was. So our premise is that if we go to a mountain peak if we're some distance away from a mountain peak and we calculate our relative angle to that mountain peak, just based off of the raw trig on what that peak would be, assuming no globular drop, what's the difference in altitudes? And would that correspond to a different occlusion timing? Because as we know that occlusions are a physical process. So by doing a little trig, we can compare what angles would have to intersect with the stars. So we go to the mountain peaks in Stellarium and we reference the true position of the star. And whenever the stars are intersected at that angle, we write down that time. And us, the observer on the ground, X distance away, if we suddenly stop seeing the star at that exact time, then we could start drawing some triangles that can determine our distance and even the elevation to the mountain. And we're going to compete with what the globe predicts without first giving our location to the globe. Like, that's the real power of the system, is that using trig based off of the occlusion timing and the peak, using that elevation, we can backwards derive what the distance would be. All right, so to start us off here, to walk us through the spreadsheet, here's a link to the spreadsheet. Everyone can take a gander at it, look at the formulas, examine it. There's no extensions or anything on the back end. It's all just in the sheet here. So our inputs are going to be, here's the little legend here. So everything in green you can edit. Grays are constant. Anything that has the Aries ram sign, is derived off of occlusion timings. So we come here, we start with the Pikes Peak example. We enter our altitude. Go ahead.
Are you streaming?
You're not streaming anything.
Oh,
yeah, you might want to do that.
Yeah, good call, brother, man.
Dumbass was looking everywhere for the link.
That's hilarious. Thank you, sir. Thank you. I'll give a second to let everyone get in. That's funny. All right, sorry about that, lads. Everyone should be good now. Okay.
Righty.
Cool. So now we got our spreadsheet here. And like I said, the link's here. You guys make a copy of it and play around with it or whatever. Anyway, what you can do is duplicate a slide and then change the name and location to whatever star and peak you're using and then edit the necessary info. But here we go. So we got altitude difference. To get our altitude difference, that's just observer altitude and peak altitude. We have our distance in meters. We have the radius of the globe in meters. And we have a celestial refraction coefficient that's derived up here. One of G.G. Bennett's from the from a celestial navigation document that I got that recommended this. for like all elevations. It's like a general it's a general correction formula. So anyway, we're going to be comparing, and we have the occlusion timing. So we have the angle which the star was no longer visible, where we're going to reference where the true position of that star was, and we're going to do trig off of that true star position. So we got the name of the star here, we got the location, all this stuff in your lat long coordinates, and then this way people can verify in Stellarium the times of occlusions and positions and all that to make sure no numbers are being fudged or anything. Now, we have the flat Earth prediction based off of the difference in elevation and the distance. So the tangent of that gives us 2 degrees and 31 arc minutes. And then from that, so we have our raw occlusion angle. So we're saying if the Earth is flat, then the true position, when the true position of that star intersects with that angle, it's no longer going to be visible. And that's what we're predicting. And then if that's true from that time, or from that angle that corresponds to that time, we can backwards derive a couple other things. But before we get to the backwards deriving in secondary and third triangles, we'll continue on to show what we do for the globe prediction. So for the globe prediction, we just take the square of the radius plus the square of the distance minus the radius, and that gives us what the expected drop is in meters. And then we convert that to an angle, doing the same tangent relationship that we did earlier. So just using this as an elevation and that distance, we get 13 arc minutes, and then we just subtract that from the flat Earth prediction. Now, what was changed from that was, because if you do that, it comes out to 217, and then people will argue that, well, you got to include this or that, and it comes out to be 219. You're doing it wrong, et cetera, et cetera. So what I changed it to was to derive the globe drop from the occlusion timing minus the expected drop in meters converted into an angle. And it comes out to 219. So if anyone has seen the, let me see here 1 second, I'll put it in the chat. If anyone's seen this from Ruhif, where he says that this angle should be 219, it should be 219. Well, it's 220 right now. I can make it to 19 by subtracting 10 from here from this. This is my fudge factor thing. So if any angles ever disagree or anyone wants to see if the globe were this or that, we could adjust it here and look. So anyway, when we do 219, same relationship here, but I'm just going to leave it as is. That's the 220 here. And from that angle based, from that based on the occlusion timing, what we can now do is get in the same way that we were deriving the other predictions, just using the tangent, we can take the tangent of the globe drop and the distance. The globe drop, which is derived from the occlusion timing, and we can get what the elevation of the mountain peak would be. And in the same respect, we do
on that geometric globular angle now or later.
Later.
Right.
Later. Okay. So we do the same thing for flat Earth in meters. We're just using the occlusion timing to get what the elevation would have to be to do the occluding. So we have the distance and the occlusion angle. The tangent of that gives us what the elevation of the mountain would be in meters, and then we subtract that value from the known elevation, and we get this. It comes out to be -49 because the star was occluded at an angle that was higher than what we predicted. So it comes out to be -49. Our distance to the peak, using the same kind of relationship, where we backwards derive the distance off of the occlusion timing and the elevation, we get we're dead on for our location. And then when we do that with the globe, when we backwards derive the occlusion, or when we backwards derive the elevation off of the occlusion angle for the globe, what we get is 2074. And the difference from that gives us 152. And what you'll notice here with this, when we subtract these two, -49 and 152, we get what the globe would predict in drop in meters as their expected drop, which is crazy. So we've independently shown that the expected drop difference based off of occlusion timings is the globe is off by exactly how much it predicts it should be on. And then We can backwards derive the distance off of that too, off of their occlusion angle and their elevation. And we get the incorrect distance as well. So the distance is off. And then down here, we have the displayed results. So we have the difference in prediction in meters. And then we have the totals of how much they're off in altitudes and how much they're off in distances. And then we continue on. So is there any questions about this analysis so far?
The globe prediction's 219. The end.
Okay. Okay. That's no problem. So here's 219. All right, so that didn't help at all. So keep in mind here. So this is what we're doing here. So this is what.
Continue.
Please.
Was that worth it
Given
though?
that Biasticles laughed. Given that Biasticles laughed. Right. Do you want me to continue?
Please.
Okay. So this, when you go to convert the angle back into an elevation, you're assuming a flat Earth for it. You need to, if we're trying to work out the elevation based on an angle on a globe, we need to account for drop and refraction. You're not doing that.
What?
It's already accounted for. You're trying to unaccount for it now that we have to measure it again. That's ridiculous.
So to come up with the prediction of 219, I need to account for drop and refraction, correct?
We already did that. That's how we got to 219.
Right. But to go backwards, I also need to account for it in the other direction, right?
So then you can use the flat Earth angle for your angle again? No, that's not how the mutually exclusive
I'm not
works,
using the
dude.
flat Earth angle. I'm not using the flat Earth angle. I'm accounting for drop.
We already
It's like-
accounted
Okay.
for it,
Oh,
and you would
excellent.
have. So Ruhif, here's the thing: you're trying to change the timing. The occlusion happened at
I'm
one
not.
time. Yeah,
Nothing.
Yeah.
This
So-
literally has
so
nothing
you're-
to do
you're
with
saying-
timing.
yeah. You're saying
Literally
at
nothing to do with
you're
timing.
saying at Mike's house, the star's at 219, right? And that's
Yeah.
also the elevation of the thing, right? So if that if that was the case on a globe, and we backwards derive based off of those elevations, we get exactly where we're at on a flat Earth, and we're pretty close to the actual elevation of the mountain. When we backwards derive it on a globe, but using the 219, it's way off.
No, it's not, because you're
Yeah.
not accounting for drop and refraction.
Yeah, we already did.
If I
That.
go
That's in the occlusion prediction, because you would have a different time. You would have a different time for occlusion.
If I go out and ignore the stars for a second, if I go out and measure 219 from Mike's house to the mountain, all right, and I assume I'm on a globe, how do I then go back and calculate a height for the mountain? What do I have to do?
This is irrelevant to the timing. You need a timing produced by an observation.
Formatting it, Shane.
No, you're just
No.
The globe yet
no,
again.
No,
you're being
listen.
retarded. You're trying to move the observer where he's not, dude.
No, listen, and also, if we were strawmanning the globe, we wouldn't be able to backwards derive our position using a quote unquote a globe tool. So we're doing something right. So what's different?
You
What's
can
the
be
difference here? No, you have the wrong angle for the Earth to be a globe based on the physical occlusion time. You just said it's not
Occlusion
220.
happens at 219.
Okay, it's 219 right there. What are you talking about?
And we're drawing our geometric relationship off of the true position of the star and the mountain peak at that time. And you're saying, and you're trying to do the same thing at 219, and you're off. So we have,
No.
yeah.
You're
And
locked
can-
into
and-
219 at that
and-
point. You can't change
and-
it after that.
And well, you can do your own thing and make a video about it and show us how. But here's the thing: you're now off, and you have to tell Stellarium. Yeah, and on top of that, you have to tell Stellarium where you're at, which is a postdiction. We can derive it from the elevation of the mountain and the occlusion angle accurately
Let's go back to
using flat Earth
something we used.
trigonometry. No, let's predict where the observer is actually at using his crosshair, which is the mountain peak. Which one of us predicts the location most accurately, and which one of us predicts the physical elevation of the mountain based off of that distance more accurately? It's us.
I do.
You-
No, it's not. No, it's not.
You seem off a little
By half
bit,
a
bud.
minute. Yeah, that's because
All
you're
right, well,
strawmanning
you're
it.
gonna say no. So okay, if he's strawmanning it, what's wrong with 219? I don't get it.
Right, 219.
That's what you've been saying the whole time.
Right. So ignore the stars just for a minute, right? if I go to Mike's house and I want to know the elevation of Pike's Peak, right? I measure an angle to it with an actual theodolite, and it measures 219, right? I have to account for, and I know the distance to it. I have to account for refraction, right? So I take off 2 arc minutes. So the true angle is 217. I know the distance, therefore I know how much drop to expect. So I've got to take that off the height of the peak, or the expected height of the peak, right? From that, I can calculate what the actual height of the peak is.
So you want to use our flat Earth
Wait.
prediction by adding in your correction to get a
How
different
am I
mutually
using a flat
exclusive
Earth
angle,
prediction?
Okay,
I've
okay,
just
and then
so-
and then
so-
subtracting it again to compare.
So hold on a second. When we use the raw when we do the raw trig of what the globe would predict for 217, you say that's wrong. It needs to be 219. I adjusted to 219.
Raw is
You're
217.
you're saying I know. And now you're saying it has to be adjusted for this or that. What number does this need to be? What number do you think this needs to be changed to? I can do it right here. What number?
Whatever. It just needs to be 219.
It's
That's-
219.
There it is.
It's 219 right now.
220.
Still wrong. So now what?
It says 219.55.
Yeah, he says
Okay.
it's 4 seconds away from 220. That's what he's saying.
Oh,
All right.
okay.
Well,
Yeah.
no. Do like 11 or 12.
Yeah. Whatever. I don't care what it
Oh,
is. Whatever your bullshit you're doing.
How many arc minutes do you want, bro? Like, what do you want? So
I
he's
just
not
want it to be
straw manning your
219.
position. Okay, it's 219.
Whatever,
Now
whatever
what?
bullshit is in that formula, whenever it's 219.
When you say
right,
whatever
you work
bullshit,
out
hold on. Let's go over what bullshit's in it real quick. So what
what is
bullshit?
the
Decimal degrees.
18 decimal degrees?
What?
What?
DD.
Terrestrial refraction. Yeah.
Oh, sorry. The terrestrial refraction thing, it was originally supposed to be like an actual coefficient thing to put in so you could like adjust the temperature and pressure or whatever for your thing, but I didn't have time for that. A much easier way was just to put in whatever value and then that'll adjust this over here. So this is just 18 and it's just making this number different over here.
Okay, that's very enlightening. Whatever you put in there, right?
Mhm.
The actual angle to the mountain is 219.
Right.
If I want to reverse engineer a height from that on a globe,
hmm
I have to account for refraction and the drop.
You have to
Okay.
use your occlusion timing prediction with the
Okay.
angle, right? 219.
Ignore the stars for a minute, Shane. Just for now, ignore the stars. We're just trying to get back to a calculated elevation based on an angle.
Yeah, we did that. So based off of 219,
Really?
you get these values over here, which is why your distances are off.
Oh, geez, do I need to do this myself?
Yes, because we're gonna move on now because you're like you're low key like disagreeing, but like you're not.
Not saying how. Yeah, you're saying it should be
Well,
219. Okay, it's 219. Okay,
I can make
So
it
what?
whatever it needs to be, and
Doesn't
it's
change anything.
it's still wrong. That's the
So-
point.
Just
So-
point out for him how you're calculating the drop. Where
you're saying it's wrong, but I can backwards derive my location and estimate the physical elevation of the mountain just off of the occlusion time and the elevation of the peak.
All right, I will do
So-
it myself. I'll be back in 5 minutes.
All right, cool. So, the Blinn Mountain ones, where this is where a simulator was used, where an idealized location was, blah, 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 blah. We get into the different analyses for, the battle of the spreadsheets, right? Who's got the right thing? Jesse recently posted a thing where he showed how he derived his elevation differences using like the focal length of his camera in arc minutes overlaid on his screen and measuring the thing with an overlay. And I do not disagree with that sort of analysis at all. That sort of where the corrections are based off of a physical process that's tangible, totally support that. So I'm using all of his custom elevations and I don't dispute any of the adjustments that he made. Totally fine. So just following the same process, right? We're consistent here. Everything we went over in this spreadsheet for the values, how things can be derived. We're now going to make the next analysis on Blinn Mountain off of the same values based off of the occlusion timings. And what we see here again is that the globe drop for Blinn Mountain is going to be 1 131 for in meters, and the difference when you subtract the these two values here, which is the difference in altitude with respect to the true altitude, you get the expected globe drop again in meters, independently verified from this process. That's supposedly straw manning. Guys, there were straw manning the globe while simultaneously predicting the globe drop. But by coming like, and that's
Yeah, I don't get
exactly
that.
and that's exactly how much the globe is off based off of the occlusion time. Anyway, so we have here the analysis at the bottom. The globe Earth is off by 268. Flat Earth is closer in the elevation by 130 or 31, and in distance we're dead on. The globe's off by 10,000 meters.
But wait, where's the fudge factor you applied to get all those right results? Hold on.
Nowhere. As you can see here, the refraction thing is turned off. This is all just derived off of the raw occlusion angle. So we have a couple other stars at Blend Mountain at different elevations. So this one was at 650. This one's at 43 at a different distance. So slightly different angle here, but same mountain peak. Again, Flat Earth is closer by 38 meters. Globe Earth is off by 111. Flat Earth's dead on for distance. Globe's off by 1,600 meters. And again, the distance, and the exact amount that the globe is off again is exactly how much it predicts as a drop in meters. Here's Blend Mountain again from another different elevation. Same situation. It's close, but it's not there. It's almost indistinguishable. And again, this location was specifically picked to to do two things. One, show the Earth as a globe, and secondarily invalidate the methodology and show that it's not a valid method. Now, if you ask Jesse if he used the actual if he lined up the peak with the true position of the star at the time, he might tell you yes or no depending on who he's talking to. But the answer to his question is both. He validated our methodology and also trying to use a spot that showed the globe. So what he did here, what we'll look at on the mountain peak, we have the position of the star at 240 at 42 arc minutes. And then when we go to the apparent, or when we enable apparent position, it's at 1 degree 5 arc minutes, but that's irrelevant for right now. When we go to observer location, the star's true position is at 20 arc minutes, but the refracted position is at 46 arc minutes. So what he did was find a place where the drop is the same as the refracted correction, essentially. So like he can say that he did the globe testing method the way that they want to move to where the observer is at, and then look at the star the way that Ruhif's trying to argue right now about how this has to be 219. Great. Well, when we do that, your guys are off. You're always off. So this whole analysis and fighting between spreadsheets and correction values, this is the most straightforward analysis we'll ever get. It's all done with just arctan. It gets nothing beyond that, and we're just comparing what the elevations are based off of the occlusion timing.
The globe is locked into a refracted lower triangle, which is what we're analyzing, and they don't want to accept that. He wants to predict it to be different, and then as soon as you want to start measuring stuff, he wants to correct it to go back to what it was before the corrections so that it would make sense, because he understands that anything to this lower refracted triangle is going to be wrong, right?
Yep. Yeah, what you're going to see here. So again, this was just more blends at different elevations, and with respect to the occlusion timing. So he was adjusting the elevation of the peak essentially to fit where the occlusion had happened. And again, if you want to do that sort of thing and you could back it up with a real world thing and have a ratio to your focal length and all that, like, I'm not going to be like, no, dog, you can't do it. Because I support that. So these are totally fine. So we absorb all the Blend Mountain measurements. Now here we have an interesting one. This is Houndstooth. This measurement was done by Catalan. Shout out to Catalan. And what we have here is the closest on record globular measurement, ladies and gentlemen. The difference in predictions here was 6 meters. And Yeah, they were super close. So in elevation, they came out to be -12. We were closer by 6, and then we're spot on for distance. They were off by 33 meters. Unlucky. And so this was done at an angle of 10 degrees. Anyway, here we have another one from Goose. This is at sea level, similar to Jesse's measurement, where the observer elevation isn't very high, but the peak was higher. But here it's very close. Flat Earth 22 meters, globe's off by 40 meters. Flat Earth distance is dead on. Globe Earth is off by 263 meters. And let's see here. We got Blodgett Peak. So we went through 1 star for every peak. And then, you know, we can obviously add more or whatever on the fly because it's pretty straightforward and easy. But to get us all started, we're just looking at a sample of every peak to give you an idea of what this is supposed to represent. Remember, we're backwards deriving the mountain elevation based off of the occlusion timing and the distance. And here we're backwards deriving the distance using the occlusion timing and the elevation that we got off our occlusion timing.
It's 3 parts of a triangle.
Yep. So we're analyzing 3 separate triangles here. We got our prediction triangles, and then we got our elevation and distance triangles that we're comparing based off of the, you know, all derived off of the occlusion timing. I say backwards derived a lot, but it's actually, you're just deriving a triangle. There's nothing backwards about it. It's just, you know, 2 parts of the triangle, you solve, you get the other part. So anyway, so again, the globe's off here for Blodgett Peak. Flat Earth is closer in elevation by 100 meters. Globe's off by 140. And then they're off in distance by 4,800 meters. Mount Rosa, as Man of Stone would say, Mount Rosa, very passionately. Another flat Earth one. You know, globe's off by 182 meters. Off, and then they're off in distance by almost 6,000 meters. And then again, the difference in how much they're off, right? The difference from our prediction minus what it actually is 4. The difference in what the globe prediction is comes out to be 108. You subtract those. Oh my God, what's that? It's the globe drop in meters. How is it that we're using star occlusions and the known distance to backwards derive everything and compare, and we're getting what the globe predicts as drop? Curious. We have Blue Mountain here. Same situation. Globe's off by 10,000 meters. It's off by its drop amount, or the difference in drop amount is what the globe predicts as actual drop. And here we have the flat Earth prediction in altitude. We're closer by 194 meters. Green Mountain. Where's the which one is that? Green Mountain. Same thing. Oops. Did we do Green Mountain already, or was that Blue Mountain? I can't remember. Anyway, North Peak here. So here we got this North Peak scenario where the globe is off by 79,000 meters. That's unfortunate in distance, and 800 meters in elevation. And we added the stars that were in contention where it said that, what's the argument? That this result gives a concave Earth because this was occluded at Green Mountain, and if you use Green Mountain, it's 2,000 feet above it, yada yada, right? Well, whatever you optically see, this is why we're using the true positions with respect to occlusion timings. Is whatever we optically see, when you derive it with respect to the peak of the North Peak, not changing anything else, just instead of using this elevation, we use this one. It corresponds to the other North Peak measurement, and it lines up distance-wise to where the observer's at. So we confirm that whatever happened there optically, the occlusion happened with respect to North Peak. And we have this is just plain trig analysis to back that up. Like it matches. If you want to throw it out as an outlier or disagree with it or whatever, Totally fine. We have another one at North Peak that's verified, same thing. So it doesn't, so that this methodology doesn't give tiny globe results. It doesn't give globe results. It doesn't give concave results. It gives mutually exclusive results based off of a triangle that's based off of occlusion timing using the location of a star, using the system where they have the positions of the stars based off of a snapshot in time and then moving them at 15 degrees per hour. So this is the only time anyone's ever used the quote unquote true position of a star for anything. Is no one's ever used it for anything except for us. And when we do it, we can show that the Earth is measuring flat with respect to the stars. We have Cheyenne
Coplanar.
Mountain. Yeah, we have a couple more. That is the implication with this, right? Is that the stars are coplanar with the Earth. So we got a couple more to get through here, and then we'll take Q&A or whatever, get into Q&A. So Cheyenne Mountain, same situation, globes off by the difference in occlusion elevations. And then when we get down to the closest elevation prediction, flat Earth is closest by 142, globes off by 204, and then distance-wise, the globe's off by 8,000 meters. Super unfortunate. And then we have Getaway Mountain, the globe's off by 14,000 meters, almost 300 meters in elevation, and the difference in how much they're off in occlusion timing is how much the globe is predicted in horizontal drop. Any questions?
I think Ruhiv has his stream open.
Any questions besides Ruhiv real quick before we waste endless hours or whatever?
Yeah, just one from me, actually. More of a request than a question. Although, of course, it's always in the form of a question. I'm hoping you guys are all right with getting just a little more meta with the data. As succinctly as I can put it. I've seen you guys plot from left to right, everything you're doing from tabs left to right here. You know what I mean? Originally, you've got the big blue line going through the middle, the one that Rue last reviewed on the beginning of his last video. You guys know the chart, I'm sure. You show it every Monday night. If you could make another graph based on the data that we're seeing here, but the only points that we need is along one axis, we're talking about the flat Earth geometric trig angle. You know what I mean? The one that's over here, occlusion angle, B7. You know what I mean? Take that on one axis, maybe X, and on Y, the two values that you've got at the bottom in terms of the differences, the flat Earth difference and the globular difference away from that trigonometric flat Earth expectation. You know what I mean? The things that you've been plotting already, site to site, but I'd like to see it plotted against angle. Does that make sense?
No, but I will get with you later.
Man prediction or not?
Yeah, hold on one second, Rue. No, but I'll get with you later, Stone, and we'll make that happen.
I guess start it back up. I
Anyway,
didn't feel very good.
All right.
Okay. Okay.
Yeah.
We can talk about it later. Sure.
Yeah. Someone's hot micing, and
I got him.
Okay. All right, Ruhif. If anyone has any questions before Ruhif wants to get to his thing. All right, go ahead, Ruski. Let me bring you up on the screen here for me. Go ahead, sir.
My Excel showing?
Yep.
Yep, cool. So this is me deriving the height of the mountain purely from its distance, observer height, and the star occlusion. All right, and guess what I get? Like 8 meters off.
Maybe you could zoom in and put more of that on the screen. You know what I mean? There's a lot of white here we're looking at. I'd rather see the figures.
There we go.
There you go.
All right, so this is the actual occlusion angle according to Stellarium. And I reverse engineer those inputs.
No, no, it isn't. You're using someone at the house, not at the mountain.
Right.
218 is not 232. You have to use 232 to compare to what we're talking about at the actual occlusion. You're doing something entirely different here.
Do I have to tap the fucking sign chain?
You just keep sneakily trying to do something different and call it this. Like that's not. You're not doing anything related to the. And don't
I'm not
participate.
doing your bullshit.
Because this is not what we're doing.
So you actually don't have a rebuttal. You're
no.
just basically what? What are you doing?
The rebuttal is, right? The rebuttal to the celestial theodolite is that it doesn't work for Jesse's observation, which he planned to make it not work, right? That's why he chose what he did. Right? And you guys are just throwing it away. Ignoring
No.
oh, refraction.
No, we're taking it.
Oh, sorry. My mic was muted. No. We turn your attention to my screen share.
Yep.
Yeah, we don't deny anything about Jesse's thing. While you were muted, I was praising him on his derivation of the difference in elevation per mountain peak thing. So it's fine.
Per star occlusion. Yeah.
So here we go. All of his measurements, right? When we backwards derive based off of the occlusion timing, none of it agrees with the globe. You guys are off in distance and elevation.
Which is why you specifically don't derive it based on the occlusion time. You try to throw in optical angles by moving the observer back to the house and then not mentioning it. When you're like, look, I did it. Like, what?
Do I have to tap the sign again?
I mean, I don't know what that means.
The method is angles.
Is that an expression? What the hell is
angles
that?
based on occlusion times. You don't get to choose your occlusion time as 219 and then not use it like that. That's ridiculous.
The occlusion time, we all agree on the occlusion time in hours, minutes, and seconds.
The angle derived at the mountain, and you're looking at the angle from the house. That's what you keep doing.
And keep in mind, hold on a second. Big distinction here is we're using the true position time. So is the true position of the star 219 or is it 204 there? Because if it's a different time, you're doing you're doing an entirely separate analysis on top of being wrong. Yeah, you're not even following our methodology. Jesse at least followed our methodology.
Of your methodology, the falsification of your methodology is Jesse. Right?
No. Do something totally different.
No.
Is that what you're saying?
No. Turn your attention to my screen, good sir. This is the true position of the star at the elevation of the mountain, 242. This is the.
And what's the raw flat Earth angle?
42.
242. Or
no, 42.
Or I'm sorry, no. They're all. Listen, look, it's 54. That's the optical, right? When we derive the elevations.
No, that's not the optical.
Yes. Listen, that would be this. What I know, but what you're trying to compare it to globe wise is the optical angle. So if we were to compare this as an optical angle, that's what you're making the comparison of. But hold on a second. That's why there's a second part of the celestial theodolite that this is where we're using a different triangle now, because we have an occlusion time or we have an occlusion angle and we have a distance. We can derive what the elevation of the mountain peak would have to be. So when we get into that analysis, the globe is off.
So there are two things that we keep jumping in between, and I don't think you're aware that we're jumping in between. All right, there is one thing, which is the celestial theodolite supposedly giving accurate results for a flat Earth. Right, I don't care what the celestial theodolite predicts for a globe because it's bullshit. Right, so the fact that Jesse's observation is off by 12 arc minutes there, right? Whatever that discrepancy is, it breaks the celestial theodolite. Right. The second thing is what the actual globe predicts.
Ruhif, how come I could derive my location, and also how come I can derive an elevation for the mountain that's closer than what the globe predicts based off of the occlusion timing with using the true position of the star? I'm not strawmanning anything. Hold on a second. You don't break. Nothing about this breaks the celestial theodolite. The true position of the star was intersected with the physical peak, just using that timing, 42. Right? What's that? Yeah, so 242.
42 was the true position?
Right? Yes. Yep.
And the raw flat Earth angle is 54.
Yep.
Right. So your error is 11.5, 12 arc minutes, right?
But we don't care about the optical angle, though. Remember, we don't care what that difference is.
Angle. That's the raw trig angle.
Yes, but the way that you relate this 219, like when we go to Pikes Peak and you're like, hey, stop, just listen. When you're like, oh, 219, and we're saying 232, you're saying that we agree that optically this would be that this 232 looks like it's 219, but this 230 would be the raw trig, like you're saying. Now, but what you're trying to do
Is that
here,
not the celestial theodolite comparing 42 to 54? Is that the celestial theodolite?
yes.
Yes. So it's off by 11 and a half minutes.
And when we derive the elevations off of the occlusion timing, it's closer to a flat Earth, and it's dead on for the distance, which is what matters.
Again, fuck. Do I have to tap the fucking sign?
Yes.
I don't
Dude,
give
stop
a
saying
shit.
that. What does that even
No one
mean?
knows what that means.
Just tap.
Stop saying it, bro. Just say what you want to say.
Celestial theodolite prediction is. I do not care what your.
If
bullshit
you
prediction
don't
is.
care
Then
about
don't
it,
engage, dude.
Then what are you doing here?
If you don't care, Ruhiv, then like disengage, because I can accurately
I think
derive
I
my
will.
position closer to what the globe predicts using this methodology.
Yeah, with your bullshit straw man.
So then with the Ruhiv methodology, we can do a different rebuttal later then, because that has nothing to do with this.
Yeah.
I think I will disengage. Right. Your celestial theodolite is off by 11 or 12 arc minutes. That destroys it. If you do it properly with the globe, so not pretending we don't have an atmosphere and not moving the observer to some location he's not, it all works fine on the globe. The end.
So accounting
No
for
puddle, actually.
accounting for atmosphere, right? We, make the same exact measurement, dude. It doesn't matter. There's nothing else to account for. You still have a different timing to have. That's the whole purpose of this.
Fucking Christ,
Dude,
Alan.
1 second, dude. You're not going to get mad and start talking like that. And like, just, if you have nothing to contribute, just leave now and save some grace, dude. Don't be ridiculous.
I'll have one sentence and then I will actually leave. The angle to Pikes Peak is 219, and according to Stellarium, the occlusion happened at 218 and a half. That is an excellent.
My God.
No.
Okay,
That is incorrect.
no. That's fine. It is correct, but that's a post diction. That's the beauty of this. All we told Stellarium to start with, guys. This is why he's so mad and can't actually engage with it, right? This is the big distinction here. All we started with, remember, was we entered Stellarium's for the mountain peak, and we entered the angle that we derived that was our relative angle based off of our distance, and we just looked for what stars intersected with it. That's all we did, and we can backwards derive our distance and closely approximate the elevation. That's the purpose of this. That's the analysis. Saying the observer, different location. Look what happens when we use the number, the 219 that he wanted. He was like, change it to 219. We did it. It doesn't matter. And then he calls this BS. If I can find my location on the quote unquote globe with this using the globe coordinate system, then this isn't BS. This is dead on balls accurate. If you use this using the globe accurate or the globe angle, you're off. The globe and how much is it off by in occlusion timing? Dude, how much is it off in occlusion timing in meters? What? Oh, it's off by the same amount that the globe predicts for drop. That's not a coincidence. That's not a coincidence, lads and ladettes.
When we do predictions, when we can confirm them in Stellarium, there's a third-party objective observer that confirms our prediction is accurate, right? When they coincide, we know we're doing it right. Conversely, at Jesse's observation at Blind Mountain, Jesse got a different prediction than Ruhiv got a different prediction than we did than Stellarium. It was all different. So who has the authority on the correct globular prediction when these two are doing their own thing and ours agrees with Stellarium? That's really what it comes down to.
I went into Stellarium, verified his angles, put him in here at his elevations that he said, and this is what we're looking at in the analysis and difference in elevation based off of that occlusion timing. Yep. For all of his stars, that's what I did. For every single star, I didn't do anything different. There's no crazy trickery. Everybody can look at this and analyze it. It's all arctan over something. There's not a cosine to be found. What's up?
So I think we should highlight something very important. So when you're talking about the occlusion timing is equal to an angle. Right?
Yes.
The timing equals to the angle.
Yes, the latitude and longitude system is dependent on that.
Right. So when you have one occlusion timing, your angle is basically what it says. It says 230. What was it for Pikes Peak? 234? Something of that nature?
Yeah. Yes.
Right. Now, if you took that angle, right, and then basically got the other two parts, like the height So if you have the angle and then the height, then you can derive the distance. And then vice versa, etc. So when you take the angle that he's saying, oh, it's actually 219. If you were to derive the distance, it would be way off. It would be 5,000 meters off. That triangle would be off. And then the height would be exactly what the globe predicts as drop, being off by that exact amount. That's the significance of it. That's the crazy part. It's like they're not only wrong, but they're wrong by the exact amount that they predict to be right.
They're wrong by the difference in their drop. It's crazy.
Can I say something?
Absolutely.
It would be nice to have like you and Ruhiv take like the raw values and do the math side by side to see like where it's differing and what the significance is of that.
We have that in
It would be
Jesse's
nice.
spreadsheet where they
Yeah.
put all their predictions side by side and they're all still wrong. That's why he changes the method and invents new things and uses different values to try and pretend that the globe is right. The only way he can is by changing everything.
Yeah, correct me if I'm wrong, but that was the whole point of why you guys have done all these measurements and all these discussions in public, streamed it all, discussions with Jesse and Ruhif about how you're going to do this over the last 7-8 months now.
That was the exact purpose of it.
Yeah, Ruhiv's position now is, well, I'm not going to use your method. Well, it's like if you're going to challenge it,
Remember,
then
it
you
used
should
to be a
probably use it.
coincidence. Remember, it used to be a coincidence. And then remember, we said, Jesse, you're using a simulator to cherry pick. He said, I'm not cherry picking. My dude just said his entire purpose was to cherry pick it to destroy the celestial theodolite. And even in doing that,
he happened to say that in passing.
and even in doing that, the globe's still wrong, guys. He used our methodology to validate it, no matter what he says. Like, here's the thing: at the mountain peak, true position intersected with the did the occlusion. That's the angle that we're using for when the star is no longer visible, and this is what it derives out to be. Calling that BS is insane, because when they try to do it, if they were to try to do it using the apparent position at their location, then they don't get the results that we do and we win. That's the significance of this. This is why he's freaking out, saying we're doing it wrong, calling it BS. It can't be BS if we can derive our location and closely approximate the elevation, the physical elevation of it. This number here being off in the prediction isn't the significant part of it. This doesn't break the celestial theodolite. This is the approximation based off of raw trig at that distance based off of the elevation. Now, the thing with that is, though, once we have the occlusion angle, that physical intersection point, we now know that is that's the physical elevation of it. So it's like, okay, what does a globe predict using the physical elevation versus a flat Earth? Oh, look, the difference is flat Earth is still closer in elevation prediction, dead on for distance. The globe's off by 10,000 meters. Imagine you were off by 10,000 meters for some reason when you try to account for a globe, but when you just do raw trig with a flat Earth, it's dead on or closely approximating the elevation.
Yeah, can we actually just stay on there real quick? So you have the occlusion angle, 40, the actual occlusion angle in terms of the true geometric position, or the true position of the star at that exact time, 42 arc minutes, 37 arc seconds, right?
Mm-hmm.
And then using that, you basically, you're using that occlusion angle, and then what? What do you do with that occlusion angle? Do you have a height or do you have a distance, right? Like which one are you? Mountain altitude based on occlusion time.
Yeah, mountain altitude based on occlusion time is the tangent of the geometric globe angle and the distance. And the geometric globe angle is the occlusion angle minus the elevation in meters converted into an angle. And then it's obvious,
Right.
then it's adjustable over here in case somebody doesn't like it. We could use this over here to make it whatever they say that the globe has to be. Because we're only doing triangles here based off of occlusion timing. If there's a disagreement on what the globe predicts, we can change it to whatever they need it to be and the analysis like can still proceed.
Yeah.
Forward.
And then notice on Blinn Mountain. So the reason why Jesse used these numbers or used this distance and this mountain peak and this occlusion time is because if you look at the celestial refraction number,
it's 23 arc minutes in celestial refraction.
Right. So, and then if you look, that basically adds 15 or so arc minutes, or no, it adds 24 arc minutes of refraction to basically bring it back to the arctan of rise over run, which is basically 54, the elevation angle, like just a plain trig. So he's using refraction to bring it back up.
Well,
and it didn't work.
And it still didn't work because you have a different distance.
Remember that the G.G. Bennett refraction formula, if you do the graph that he put in his paper, you can see at the horizon it's strongest, right? So he knows, that's why he said he set out to do this. I'm going to find an actual distance away where the refraction will equal the Earth drop, and my prediction will be indistinguishable from flat. That is the actual process that Jesse followed to try to quote and validate it, right? So by using the refraction coefficient closest to the horizon, and then we have our buddy Ruhif, who won't argue optical elevations at ground level because he's the 7/6 R king with his weather balloons. He says, get up about 100 meters. Why? Because he'll argue infinite refraction and the coefficient and be able to see your own ass at the surface. That's why every surface-based observation argument is null and void because of infinite refraction up to 100 meters. But then we have the same people saying that actually an observation within that zone, right on the horizon below less than a half a degree, well, actually that invalidates the whole thing. Not a word about refraction. Just saying, just to put it into perspective.
Yeah, I've got one comment and then I've got to go. Can you hear me?
Sir.
Yeah, what's up, JT?
Okay, so finishing up a long trip and I got to conclude with this, and it was amazing. What this is tied together for me in a beautiful way is earlier, Alan, you said that the stars above and the Earth are coplanar. And that means that the stars actually run parallel to the Earth we live on. It just optically appears to drop because of how, we see things visually. The same thing applies like to train tracks. They converge in the distance only optically, only visually. It sure looks like it in pictures and when you're standing there, but we know that train tracks run parallel the whole time. And when I see a white fluffy cloud day and I see those clouds just off in the distance smashing into the ground, it's the same thing as the train tracks, but with this celestial observation, this whole thing you've done is you're just taking refraction out of it, the confusion of refraction that the globe throws, and also the whole debate over perspective. Is it real? Do boats disappear bottom up? Blah, blah, blah. You're just making it to where it's simply an exclusive proof or evidence, and I'm loving it. So thank you for what you're doing.
Thank you, JT. And yeah, you nailed it. The occlusions are physical, so whatever the elevation is when it physically intersects, that's what we're using. That's why we use it for both our predictions. We compare the globe, we compare flat Earth, and then because it doesn't add up to the globe, suddenly we're strawmanning the globe. It's like, all right, dude, peace be upon you, brother. But check this out, JTZ. Are you in the screen share? Can you see this?
Let me scroll up just a second. All right, so now I am. Go ahead.
What we're looking at is a model made in the late 1800s from a Japanese fellow who was demonstrating the stars being coplanar above us. So the stars go on this top fixture here and they rotate on this cogwheel, and the cogwheel goes up and down in elevation. And down here, there's little celestial hemispheres that represent your, the hemisphere that you see of the sky. And as this rotates, the projections that you see over top, as the elevation goes up and down, you see a change on the little celestial domes. And this whole device was made at such a ratio when you crank the wheel to do the rotations. Each latitude would get the sun and the moon for like 90 days or whatever, and it would do like the whole rotation. And this model, like when you look at the diagram that they had, they knew all about the South Pole, North Pole, and these guys were all flat Earth geocentric cosmology, in the late 1800s when when the Jesuits came over and proposed the solar calendar and all that to them. But even dating back to the 1400s, there was a Chinese expedition that was done where they were using a Peri-Reis map, which is just a rhumb line map to navigate. And they apparently, I gotta look into the documentation some more, but they went to Antarctica, they went all over and sailed, and they were all a part of the same flat Earth cosmology as the Buddhist monks from Japan as well, because they were Shintaoist, I think, but the cosmology is the exact same, like planar Earth, the dome over top, etc. So this model in particular represented the 4 known continents at the time, and then how they would see the positions of the bodies relative to their seasons. They made an actual physical model. This was on display at the Japanese World Fair for a number of years, and I think it's still on display somewhere now. But
It's
yeah,
dope.
but yeah,
Man, that's super cool, Alan. I've never seen anything like that. And to me, when I look at those 4 different pods, if you will, the azimuthal grid of vision, if you will, for those known
Yep.
continents, what we know now is each individual person has their own individual grid of vision. So, like in my hometown, when the sun is about to come up, and the whole side of the sky is lit up before the actual orb of the sun appears, it's never down below my feet, and it's never even low. It just optically appears to me to rise to the zenith and set over as the stars do as well. But it's all the plain earth and the plain heavens. And people have got to get a grip with that being reality. And if you keep pushing the type of logic and measurements that you're doing and just staying firm and not getting pissed, you've got it in the bag. And like I said again, huh? Somebody's hot micing.
Yeah, I got it.
Yeah, JT.
Anyway, I
I
think
like to
it's
play.
freaking awesome.
I like to play a game of who did it first: Walter Bislin, Shane St. Pierre, or all the Asians.
All of them.
It turns
awesome,
out it
y'all.
was all the Asians. Then it was Walter/Shane. But since the Asians did it first, I don't think anyone owns it mutually exclusively. But yeah, they were all navigating on a celestial sphere model, knowing that the apparent positions of the bodies is all anyone sees at one time. They weren't like, oh no, the star is beneath my feet. It was just out of their vision.
They were metaphysical with it, and then Newton was like, nah, it's physical, and I know how everything works, and mass attracts mass, and follow me, by the way.
That was exactly the battle that they had at the end of the 18th century, at the end of the 1800s there, where the basically, they were like, we already have everything. We have our own calendar. We have our own this and that. We can navigate. We already know, like, what do we need your stuff for? And the big argument for the Jezzies was that they were adding Newtonian dynamics. They had the physicality of the heavens, because the cosmology that they were trying to supersede said that the heavens were like the true thing, and the world that we perceive and the world that we live in is the illusion, and we can never perceive the heavens because we're impure or whatever, what have you got to meditate, etc., kind of thing. But anyway, they knew that this was an illusion, and they actually used all the Western teachings as diagrams on optics regarding refraction, perspective, and all that to show how nothing what they're asserting about the heavens can be physically true. But they were like, but my math formula, but my GMM over R squared, and they eventually won out. But that's literally the only difference between the two. Like, all these coordinate systems work the same. It's just one's been asserted to be entirely physical with dynamics that didn't work out so well when they tried to measure the velocity of Earth through space.
Man, total fire. Where my final comment, and I am going to go, is we, true earthers, flat earthers, what's really going on with the realm we live in, people have been gaslit and told to go back to school, and just the trolls have attacked forever. And now that we have this, we should have the glow believers not coming with ad homs or their own way of doing it. Look into it. They shouldn't be getting pissed or emotional. Like, if the truth is that the earth is stationary and it's a topographical plane, there shouldn't be people being pissed. Just do the numbers, and we should have tons of globers and flat earthers taking these measurements, turning them in, because you guys have described how to do it. And we'll see more and more and more of what the truth is. So, and it's also awesome hearing Toby, brother. Good to hear from you, and I'll see y'all later.
Yeah.
Shout out to
JT.
Tobetheus.
I have a
That's a
quick
good comment there.
if that's okay.
Someone trying to
What's
come
your
in?
name?
Yeah, JT just
I
said
have
what
a
up.
quick comment if that's okay.
Absolutely.
Yeah, Lily, what's up?
Shoot.
Okay. Yeah.
Yes.
Well, the reason that you flat earthers got all your numbers correct is because the globe Earth is really locally flat everywhere at the same time. So I think that you all should just admit it's a globe and it's locally flat, which is why it'll always seem flat and the flat math will always work. But
Well,
don't forget
She's
it's really a
adorable.
globe.
well
He's
said,
adorable.
Lily.
Well said.
Dazza, were you trying to get in?
There was a couple of interesting comments made by Boston Bear and Alan about why should you, why did Roofy have a different method? Why should you try a different method? And that's the fundamental process for testing your hypothesis, is that your hypothesis is predicting something. So you come up with another way of testing it. It doesn't mean you just reiterate your process. It means you develop another process and see whether it agrees with the hypothesis. And that's what is happening here. That people are saying something doesn't feel right. Let's how else can we test this geometrical relationship?
Something doesn't feel right. No, Dad's like, if you came up with a hypothesis and then I said, oh, cool, I'm going to test it. And then I did something completely different. And then I said, hey, Dazza, your hypothesis is shit. How would you react to that? Would you be like, hey, that's when you didn't actually test my hypothesis?
Yeah, I was
proved
gonna
the
ask.
So basically, your hypothesis is
null.
saying,
Wait,
right,
wait,
that
wait.
we think the
The
Earth
hypothesis
is flat.
was proven. The hypothesis was proven null. You don't go back to testing it. You come up with a new hypothesis.
There you
Yeah,
go.
exactly. Do you remember the
But
original?
is it proven null? To have a null
Hold on, Dazza.
hypothesis, you've got to exclude all other options, right?
Yeah, to be clear, we failed to falsify our null hypothesis, and that's that the Earth
Exactly.
is flat. Our hypothesis was that the Earth is a globe. We failed to falsify. Like none of these measurements indicate that the Earth is a globe. If I can backwards derive my elevation and approximate the elevation of a mountain closer than a globe can using flat Earth trig, then the globe is an unnecessary part of the coordinate system. And that's also noted because the difference in occlusion timing elevations comes out to be the expected globe drop in elevation.
But is it because your method is correct or because of something else, right? And that's the thing. You've shown maybe that there's something in your method, but why? You don't know why.
Yeah, it's because it's flat, bro.
I know why, because we're doing triangles with occlusion timings, and the Earth's flat. That's the geometric relationship implication there.
That's the direct
You have
inference
this
at the end.
other
yeah.
evidence out in the big bad world that is directly contradictory with what you're claiming, right?
No,
You're
there's
saying
none. There's
it
none.
can't
This
be.
is the highest form because we're using the true position, the calculated true position of the star. We're actually externally.
So it's a calculated true position,
Please
right?
don't
So you're making
interrupt
some
me. And you're making a mistake by interrupting me by talking. That's a huge no-no. That'll actually never fly ever. So we're not making any mistakes. Here's what we're doing. We are externally testing an internally consistent system. Everything that you're about to reference, such as GPS, et cetera, is all going to be internally consistent with the coordinate system because it's referencing the coordinate system. We have not told the coordinate system where we were at, and we can derive our actual physical location on the ground where we observe the occlusion based off of that trig angle. There is nothing that you could offer that will supersede that. Go ahead.
So you're establishing a coordinate system the minute you do this, right? You're anchoring your origin initially at the observer, but ultimately on the mountain, right? And that is your reference system for all of your geometry. And if there is another measurement of that geometry that contradicts your geometry, then one of them is incorrect, right?
Yeah, that's what I'm saying here. So when we do the globe version of this, it doesn't contradict us. That's why we're still correct. When he said we can do this different method and do this other thing, that has nothing to do with what we're doing, and that's why we don't care about it.
Yeah, but the globe measured geometry of these mountain peaks contradicts your assumed geometry of the mountain peak.
No, doesn't at all. We're actually
Direct opposite.
we're actually able to
does.
derive the. No, hold on a second. When you say no, it does. Refer to this spreadsheet. Let's take a gander at it. Let's take a look at it. We're at 39 Aquarii. The elevation that we derived based off of the occlusion timing, the time that the star was no longer visible, and we referenced the true position in stellarium where it was at. When we derive the elevation based off of the tangent which is the distance in that occlusion timing, we get this for what the elevation would have had to have been in meters. And when we subtract that from the known elevation, because the angle was higher, it comes out to be negative 45. When we do the same thing for what the globe predicts using 219, remember how we had to use 219 because 219 is the number, not 220, not 217, but 219 because you have to account for refraction, whatever. Okay, cool. 219. We're looking at 219 right here. And we're looking at the elevation derivation based off of occlusion timing using 219. Oh no, that's not, you're off by 170 meters. And then also further, when you subtract what our value off of it, you get what the globe would have predicted the drop is in meters. That's crazy. But check this out. On the bottom here, the closer altitude prediction is flat Earth for the physical elevation of the mountain, and the globe is off in meters when you derive the distance doing the tangent of the elevation and the occlusion angle. You get you're off by almost 5,000 meters. So what was it you were saying again?
Yeah. So where are all of your, when you're comparing your results, where are the numbers coming from? What is the true elevation of the mountain? What is the true
It's right there on the left. It's on the left.
No, where
bro.
do they come from?
The
What
true
is the origin of that information?
The true elevation of the mountain comes from the mountain elevation at sea level. Observer location, same thing, right? Just the
where does that come from?
Latitude, longitude from their locations.
Yep. So this is these latitude, longitudes, and elevations represent geometric positions, right? Where does this geometry come from?
From a spherical coordinate system called the graticule.
No. The geometry. Where does the geometry come from? The coordinate system does not change the geometry, right? You can put any arbitrary coordinate system on the surface of the Earth. It does not change the geometry. If something is 1 meter above me, it's 1 meter above me, regardless of the coordinate system, right?
There's no, I don't understand your question.
Okay, so you're confusing a coordinate system and a projection of a coordinate system with physical geometry, right?
That's projected coordinates versus geographic.
So if we use lat-long elevation as our coordinate system, that is a physical coordinate system, right? Each point in lat-long elevation has a geometric position in space. And we can take the lat-long elevation between two locations and work out the distance just doing some vector algebra, right? Or if we had a rectangular coordinate system, an XYZ coordinate system, we'd get the same distance between 2 points, right? The coordinate system is physically realized by the geometry of the thing that it's applied to.
Were you going to use the spherical graticule to confirm your distance as being higher or lower in this?
That's exactly it.
So, if we were to transform our spherical coordinates back into rectangular,
not at all. Okay.
Okay, so if we're going to transform that coordinates back into rectangular, it doesn't change the relative positions of things in space, right? So the graticule doesn't apply here. It's a physically realized, right?
The graticule.
You're trying to have a totally
increased by elevation by 100 meters.
Listen,
your elevation is going up.
What is it you think you're trying to make in terms of a point?
Yeah,
he's trying to have a different battle over the surface ellipsoid Revel ECEF from before. He's trying to tie in what I was arguing with him before about this. It's not really related to this, unless you're going to use it to derive a different elevation.
So listen, Dazza. Here's the thing. We're testing whether or not the spherical coordinate system that represents latitude and longitude accurately represents the geometry of the Earth. And what we're finding here is that based off of the occlusion timing, it would be physically impossible for the globe to have that occlusion timing because the globe predicts it's lower. That's the actual issue at hand here. I don't really know what you're trying to say. It sounds like you're having a sidebar conversation by saying that because we're using or referencing a spherical coordinate system, therefore it's instantly a globe. If that's your mentality and argumentation, thanks for coming by. It's much appreciated.
GG.
Things here, right, is that so first of all, that angle that Stellarium's giving you is based on the geometry it has for the Earth and for
it's not.
No, it is.
Oh, okay. Well, it's not, because what it is, it's hold on.
It's a geometric model.
Dazza, if you don't mind.
Anywhere on the Earth, and it does a geometric calculation of the angle.
Okay, here's what Stellarium does, brother. Stellarium is a collection, or stellarium is basically moving the true positions of the stars at 15 degrees per hour. The true positions of the stars are derived from the nautical almanac. What they did for the nautical almanac is they took zenith measurements of stars on the first cusp of Aries, and then they just added 15 degrees per hour to them. So that's all stellarium is referencing. When we're doing stellarium and referencing coordinates, it's doing a geocentric to geodetic coordinate system transformation to relate your local time, which is which corresponds to a time for where that star is with respect to where it once was on the first cusp of Aries. That is not mutually exclusive to a globe. It's tied together with a fictitious coordinate system that requires the observer to be at the center for the geocentric coordinate system transformation to occur. So because of that, it is non-mutually exclusive. It has no relation. Because of that fictitious observer, you cannot say that this coordinate system explicitly belongs to the geometry of the ground. If you can invoke a fictitious lad, so can we. We could have our own thing, blah blah blah, et cetera, et cetera. It goes on forever. Nothing can be said differently because the coordinate system will be internally consistent. So what this shows, by not telling stellarium where we're at, and we can derive our distance and relative elevation to the mountain based off of just the occlusion angle, then that shows that the coordinate system is a flat baseline all around. And what they've done is move the positions of this. Yes, it does, and it shows that they've just moved the positions of the stars with refraction corrections to make it seem like it's a globe. Because otherwise, we wouldn't be able to derive our position. Because look, we'd be the ones off, and the globe would be on.
So I'll wind you back a bit. First of all, stellarium uses a geometric model. That's how it works. It has many coordinate systems to do this, and it takes the observer and it applies a bunch of transformations to work out where an object. First of all, it takes time. It has its geometric model is a function of time.
You just said that.
Fast forwards the model in time to the current time.
Yes, that's
Bro, he just covered that.
Bro, that's literally
Then it
what I
takes
just
the
said.
observer's position and applies the geometric model to work out the angle, right?
There's no geometric
Using
model that
geometry,
applies, bro.
and that
It's a
geometry
geocentric
includes
to
the sphere,
geodetic
yeah.
transformation. Latitude in the sky is right ascension and
it doesn't
declination,
have- it
bro.
doesn't necessarily use
It's
that
literally
model. Many of
doing,
these things won't
bro. It's
use
doing local hour transformations. Just stop. Your argument's dead end. If that's your contention, then it's noted, and we're gonna take another question.
I have a quick question.
What's up, brother?
I believe I heard you say something about the stars was warped. The current globe celestial sphere is a warp of like the truth or whatever. Was that what it seems like it is?
What? When did you say that? What are you talking about?
No. I was saying that the Buddhist cosmology, they were saying that there's like a true heavens above us, where there's like the true position of a body, but what we see optically is like a refracted position. It's an apparent position. It's not the true celestial heavens. That's what their philosophical teachings were.
All right, thank you. That's all. Thanks.
Yep,
Hey,
no
Alan,
worries.
I'm still here.
What's up?
Quick. I'm going to see if this helps paint the picture, and you tell me if I'm right or wrong. So the mountain, any mountain that we're talking about on the spreadsheet, at its location, we know the height above sea level, and we know its actual height. It's not going to shrink, not going to grow. It has a height.
Yep.
So the whole important thing about this whole thing is timing. When the star is occluded by the mountain, we know the height at the mountain. We know the height that the mountain is. Now, Stellarium doesn't know, where Mike was originally, and he just said, okay, baseline to that height when it was occluded gives me this angle, and it's a planar flat baseline, measurement, and it works out. So, like if it was a globe, let's just pretend the globe was real. The mountain would be level, and the observer would have their own level, and the mountain would be lower timing wise. If it was a globe, it would be off and different. But because the Earth is planar in nature, stationary topographical plane, when the timing of the star goes behind the mountain, we know the height of the mountain locally, and then when we know our distance, that gives us the bottom baseline. Then you get the angle to the known. You're getting rid of refraction.
JT.
You're getting rid of perspective hoopla. Is that correct or incorrect?
No, that was great, but here's a even better point, right? If you have the height of the mountain and the occlusion angle of the star, right?
Right.
You don't need to know where your distance is. you can basically get the baseline of the triangle if you have those two variables, and
Right.
if you derive your baseline, your distance from those two variables, it matches what the actual distance was away from the mountain.
Right. Exclusive
That's
evidence.
that's the biggest part. Is that
It's awesome.
yeah, you can basically have all three parts of the triangle, and Globers can put whatever angle they want to put in there, and because they're locked in this refraction argument, they're wrong.
So keep it up.
And dude, and the predicted globe drop is exactly how much they are wrong by. That's crazy.
That's sweet.
Predicted.
Yeah,
Yeah, you can never get.
Go ahead.
I might have said that wrong, but yeah.
Yeah, the
There-
difference
they-
in derived elevation based off of occlusion timing comes out to be what the globe expects in meters as drop over distance.
So,
Yeah.
hey, Alan, I just posted it in the live stream text right where you just posted. Take
Nice,
a peek at the
nice.
graphic. I just did up the graph I was looking to see from you guys while I was waiting.
Nice, nice, nice. Thank God.
But this is the data that I wanted to see.
All right, what are we looking at here? We got difference in meters. 0 being we're dead on for prediction.
That's B7 for the angle, like the actual geometric one you calculate using rise and run, your arctang, and the other two are E23, I think.
B7's occlusion timing.
No, B7 is the occlusion angle in decimal degrees.
Yeah, sorry, I meant occlusion angle. Yes.
Okay, and that's actually a trig value you worked out, although the math isn't in the sheet.
No trig value. It's just the time that the star was occluded. It's just the angle that the star was occluded at. There's no
Right,
there's no
and
trick
you're
for it.
using the angle. Oh, okay, so that's the stellarium angle.
Yeah.
The stellarium dependent angle.
Yeah, all the
Okay,
trig
so
comes
that's
from.
that's the x-axis,
Yeah.
right? That's the x-axis, and then I'm taking from your purple field in E23 the two values, the positive one and the negative one, because they're positive and negative respectively for each tab. So I've taken all 16 tabs there, and there it is. It's an interesting scatter graph on margin, wouldn't you say?
Yes. What's orange?
The flat Earth is blue. That's the positive values, and the negative values are red.
Gotcha.
Those are the globe diff values, right? Neat, hey? That the lower the angle is, the bigger the difference between your two readings, essentially. And it's a logarithmic relation, approaching 0. That's how that's looking to me.
So
I thought that is very relevant to what you guys are talking about right now, isn't it?
Yes. The bigger the angle, the closer they are together. And then the smaller the angle, the further they're apart.
No, the opposite. The opposite. What you're looking at there is the angle upward to the mountain, right? So the more horizontal the look at the mountain is from the observer point, the bigger the spread between you. That when you're looking way up at 10 degrees, you guys almost get the same figure.
Oh, yeah.
But when it's way down close to the horizon, you guys totally disagree.
Yeah. That's because where you get the most distance usually, because that's when it's the furthest away. Because the one where the angle was the biggest, we were the closest. Yeah. No, yeah. Yep.
Typically so. Just thought I would point that out. I think that's
Yeah,
relevant.
that is cool. That is cool. It matches the
Badass.
logarithmic nature of those lower angles due to perspective as well.
Nice.
Hey, how dare you flat earthers use stellarium? That is globe technology. Thieves.
I mean, oh, Anchovy, you got a question? I see a question in the chat. You want to ask it, bro? You can.
How much was it actually measured in real life? Both sides are different. Just mine's closer. So
the
in
first
real.
time-
Oh, go ahead.
I was just gonna say the first time I asked about the angles from the house to the mountain peak, You guys said you actually took that. The second time you guys said you didn't. And now this time he's saying all of it is real world observation, but I keep hearing about stellarium.
Well, the optical angle aspect of it is irrelevant, right? Like if you were to get your theodolite out and measure Pikes Peak to observer location 50,000 meters, it would be 2.19 degrees, right? And we don't dispute the optical measurement of it. Now, what had happened is Mike bought an antique theodolite, measured it, said that he got a value of 231 with it, and then everyone freaked out and they were like, "No, you're using an antique one. You have to use a more accurate one." So he borrowed his brother-in-law's one, and he took a measurement with that, and he got the predicted globe value for the optical drop. Now we are testing the distinction between the two models because our position is that the drop is optical, whereas you guys say that it's physical. So that's where the analysis comes in with this, where we're using occlusion timings because those are physical. So the elevations are going to be using that, we're going to be able to determine which elevation is more accurate.
What angle is more viable? Yeah.
Right.
Okay, but what I'm confused about is if a glober and a flat earther went out there and used the same tool in the same conditions, I don't see how you guys would get different values how you are on this spreadsheet.
No, same value. You already asked this. Same value, different interpretation.
How are you saying the same value when I'm seeing different values on the spreadsheet?
When you say different values, what do you mean? Like, what are we talking here? What's not looking right? What do we need to go over here?
Okay, so the bottom number, right? When you guys say you're spot on for peak to observer distance.
Sir.
The bottom number. Let's see. Yeah.
Yeah, the one right below that, or any of them, I guess would work.
I think he's confused on what the predicted occlusion time would be, meaning that it would be different based on the globe model, and that's where the deviation would be, not necessarily the measurements of the angles themselves.
And no one's got different results. So we just the same for 43 different observations. So,
well, I'm confused how a glober would go out, take a measurement, and then plug that into whatever their prediction is, get it wrong, and still say that it's right.
I don't know what. Okay, so when you say take a measurement, what are you referring to, Anchovy?
Well, wait. Does he understand? Do you understand that this is a spreadsheet? Those are formulas. Those are the results of formulas in those cells. So it's not that those are values that were directly entered. You understand that, right? Or do you understand that? Sorry.
No. Well, that's my contention. Is if these things aren't aligning with reality, then what do I care?
Oh, they do align with reality. I can accurately derive my location and accurately estimate the physical elevation of a mountain peak with these. So it's, if you use a flat earth versus a globe, if you try to use a globe, you're going to be off. So like reality is being described by the occlusion timings and by the occlusion timings, and it's indicating that the sky and the earth are coplanar.
So what value, like what part of the formula are you guys claiming that the globe is getting wrong though? Is it the angle to the mountain to the star? Is it the height of the mountain? Like at what point is the number wrong?
Got you. So this number over here, this occlusion timing. So in order for the earth to be a globe, the mountain peak has to physically be lower because relative to the observer, the earth's curved, it's going to be tilted away. There's going to be missing elevation from it. We can calculate how much that missing elevation is, and we do. And so that's going to result in a different time. So if the earth is flat and that means there's going to be no drop in the mountain peak. So if we take the information that we know about the mountain peak and our location, just our elevation at sea level and the mountain peak above sea level, we could subtract that, get the relative altitude of the peak, and with that information we could calculate an angle to the peak based off of the distance to that. And then so that distance based off of the tangent of that will be our raw plane trig angle, assuming no elevation difference. And then from that we could subtract the difference for the globe in meters, which we do, to get what the globe would be. And these correspond to two different positions because using stellarium, using the globe, using cell nav, all that, time equals angles. So with what that means is if the mountain is physically lower in elevation, then the occlusion time that right here is going to be a different time, which is going to equal a different angle. But what ended up happening is the observer on the ground, 50,000 meters away, observed the star being occluded, and then he looked at what time it was when it got occluded. It was 6:43:07. He went into stellarium, went to the mountain peak coordinates, looked up that star, turned off refraction so he could reference the true position, because that's all we're interested in. And that true position happened to be at 234, which is much closer to the flat Earth prediction of 234 than it is 219. And then when we go to do some more trig, based off of the occlusion angle and the distance, we can get what the elevation would have to be. We subtract the elevation from what the known elevation is, and we get this number here. And because the angle was a little higher, it comes out negative for this. And then we have the drop over distance for the globe. We have their timing difference. We have their elevation derived off of the timing difference. Derived off of their globe angle. And that gives an elevation that's low, that's off. And when we compare the two, these, we get 170. And when we subtract these, it comes out to be 201. So the globe's actually off by the expected drop.
So both sides would agree. You guys both agree that the numbers on the left are all accurate. It's the numbers on the right where you guys disagree.
Yeah, the numbers on the left are all accurate. The numbers on the right are all accurate. Ruhif asked me this number, if I don't adjust this number right here, it'll be 220. But Ruhif insisted that it's 219. So I went ahead and changed it to 219 for him. When I changed it to 219, nothing, like it didn't change the outcome of this at all. But we agree on the 219. And then I guess where we stop agreeing would be right here where we derive the elevation based off of the 219, because that's where the globe starts to be wrong. And then when we derive the distance off of the 219, that's where the globe starts to be wrong again. And that's where we disagree. Up until this point, everyone's like, high-fiving. Up until the results kick in, everyone gets upset.
Yeah, you're basically checking the triangle after you have the occlusion angle, right? After you have the actual occlusion angle to the star, which is what you're using stellarium for, right? To reference the true position of the star at a certain time. You take that angle, and then you basically have the height of the mountain, and then you can get your distance based off of those two numbers. The distance comes out to 50,700 meters when you use the occlusion angle plus the height of the mountain, right? But when you use that 219 and the height of the mountain with the glob, the height of the mountain, the 2056, right? Then your distance is actually going to be wrong as well. And in reality, we know what the actual distance from the mountain is, right? Because in reality, that's where the observer actually was. So that's how you can reference which one is more correct.
I get the breakdown. I guess where I get confused at is how globe astronomers would not recognize that either they or stellarium is off for this many years.
Dude, they just use refraction to reify their globe.
Stellarium's not off. Like we're using the true position and then just adding 15 degrees per hour from that. All navigation, all use of the latitude longitude system is based off of that. There's nothing wrong in what it's reporting. Its angles are going to be at the correct timings. What's happening here is that astronomers aren't using stellarium to measure occlusion timings with respect to mountain peaks. No one's ever done this before, as far as I know. Mike Heffron was the first person to propose this back in February. And then since then, Jesse, myself, Kat, and Goose and have all participated in making the measurements. But there's nothing, like no one's going to use stellarium and then find that stellarium is wrong in that way, because the system's internally self-consistent. So if you tell stellarium where you're at, and because angles equal time and time equals angles with this coordinate system, you're always going to get the position of the star that you can visibly see. So that doesn't, nothing about that is going to be inconsistent. What is inconsistent here is if the geometry of the Earth were a globe and the curvature wasn't optical, then these mountains would physically get occluded at a later time, and their flat Earth would be falsified by that. Like, I would be here arguing for a globe, and it would be super easy because this is a triangle, and it's hella hard to argue against Pythagoras.
Yeah, I think the only thing that would like clarify this to me is what someone, I forgot who pointed it out, was for you guys to do the math side by side and see where the differences actually came up. I think that was Taylor, maybe.
That's what we just did, though.
Yeah,
That's literally what this is right here.
so the difference though side by side, right? These are all every formula in here that does an angle is an arctan, and the angle that he wanted to compare was 219, and we do that and it gives this. He's not doing an analysis where he's deriving a distance and elevation based off of the occlusion timing. He's doing something separate. That's why we asked him to leave, because it's like, if you're not going to address this portion of it, then there's no purpose for you to be here, right? Because like you want an answer to this, right? Like, so do we.
Yeah, well, that's what I'm saying though. As the audience who hasn't done this for themselves, I think it would be helpful to see at exactly which point what is his justification for the math being different.
Yeah, so when we asked him, he just said
question, bro.
He just said it's rubbish. I disagree. You're straw manning the globe. Like, the only like that's
hit
low
the sign, whatever that means.
Yeah, that's low key. That's called gaslighting.
Because all of us can look at these numbers and inputs, but we're not seeing the actual math being done on the backside.
Yeah, I got you. So we can go over it right now. We'll go over it one to one, just so it's clear.
It was covered in the beginning too, so just to be clear.
We can do it. We can do it again.
To be clear, you can go over it if you want, but it's not going to solve my issue of
how can I help
why
you
he's
then?
getting a different number.
You just don't like it because Jesse said it's wrong, right? Is that what you're saying? That's a great argument. I
that's-
appreciate
No,
that.
No, that's not the argument. I'm just
Anchovy's
curious. I'm just curious where the difference is coming from, because somebody here is wrong, and I'd like to know what their exact logic is for why that is.
Yeah. So,
because you can give me your numbers all day, but it's not going to solve my issue of why his numbers are different.
well, then you'll have to go talk to him then.
He does something completely different. Like, he doesn't disagree with the geometric Earth curve that we add and subtract. He doesn't disagree with G.G. Bennett's celestial refraction when we apply it. He disagrees with the results because they don't come up with globe. So when he doesn't, when they go and do something else, they're not saying that they disagree.
And to note, he only tried to agree with it when he thought that it proved the globe. Remember, like, he was like, it's rubbish, and it also proves a globe, and it proves it doesn't work. That's so, like,
disingenuous.
Like, what does that even mean? It does all
There's
three.
no real disagreement when you do the math. There is no real disagreement. So,
the disagreement
that's
comes. Go ahead.
I've been hearing you guys say that yours is closer. Wouldn't that suggest that some of your math is off from what we're observing?
Only in physical elevation, right? So it's like, what is the true elevation of that mountain peak? Well, it says here that, like, for example, for Pikes Peak, they say that it's 4,300, and relative to the observer, that gives 2227. And so we're getting occlusion timings that are 50 meters off. Our math isn't off. The occlusion timing is what the occlusion timing is, and the elevation of the mountain is what the elevation of the mountain is. So when we go to backwards derive the elevation based off of the occlusion timing, it's going to be based off of that. We're 100% on always for the distance, and we're pretty close and closer than the globe on elevations.
Right. Yeah. I don't doubt that you guys know how to do math, plugged into a formula. But my problem is if either something's off, if the formula, if even your formula, your number is off to what reality is.
That could be simply a difference in, if you think about a light source at a long distance, the difference between that light source touching the peak of the mountain and the light source fully being occluded. So it could just be simply the size of the light source itself. That could be that slight deviation.
It's also mostly where on the mountain is occluded, because you're calculating for the highest peak and the elevations are given at the tippity peak. But if like the lower right shoulder or left shoulder is doing the occlusion, you have a difference in the elevation, which allows for discrepancy.
Yeah, the main point of it is the distance always comes back to the observer, and you don't have to tell Stellarium, you don't have to reference the system internally to find that out, and that's huge. And on top of that, we can predict the physical elevation with the occlusion. It more closely corresponds to a flat Earth than a globe. That's the point of referencing the occlusion timings, right? We have our prediction, they have their prediction. And then when the occlusion timing just so happens to match our prediction, and we can backwards derive basically the geometry of what did the occluding in our distance, whereas when the globe tries to do it, they're going to be off by 5,000 meters, and they're going to be 170 meters too low on their peak.
Now, Heffron did sort of correct this to say what you were just saying. If it worked, it should be spot on. Well, he did some azimuth corrections based on timing, and he made it completely spot on by giving the globe the biggest benefit of the doubt. We don't use that particular aggregation in our analysis, but it does work to be exactly spot on. So,
Yeah, I don't know if you remember that, Anchovy.
Yeah, I do. I just my issue is the presumed numbers of things instead of actually getting the measurements.
That sounds
So when you go
like
to measure, when you go to get a measurement for the altitude of a mountain, the height of a mountain, you're going to go to various data for that height. You're going to use that. Then you're going to get the occlusion timing, and the occlusion timing is also going to give you the distance and the true height based on doing your trigonometry. So it's like, is the occlusion timing saying that whatever book you reference to determine, say, what Mount Diablo's peak height was, wrong, or is the occlusion timing right?
And it comes out right for us every time. It gives the physical elevation rather than the relative drop at elevation, and it should give the relative drop if it's a globe. We should this time should be 219 instead of 234. It should be closer to 219 than 234. That's the significance.
Right.
Yeah, like
regardless
imagine.
of what, regardless of what sources say about the height of a mountain, we're allowing the occlusion timing to take precedence for using our angle to calculate the distance and height, and so it's taking precedence. Now, when they put together the data on these peaks, these mountain peaks, were they using occlusion timing? Probably not.
Well, what were they using?
Yeah. Well, this also points out that the alleged drop over distance is purely optical, meaning the angle that they measure to the peak is based on an optical drop, which isn't going to change. So this removes that optical drop and puts it into reality, right, where you can make a prediction of the elevation, and it's a known elevation. So when you do this measurement, you get the known elevation of the mountain. Whereas if you try to measure optically the angle, that's where you get the optical appearance of drop over distance. So this completely eliminates that.
Yeah, if you think about it, Anchovy, like this, right? Let's say you use that Theodolite and you hit that mountain peak, you got 219, okay. And then you were to basically calculate the height of that mountain based off of the distance, right? Well, you would have the incorrect height. It would be 200 meters off, which is why you shouldn't use Theodolites that way anyway, which is why they're only used respectively 100 meters from point A to B to B to C, because of these optical effects between you and the mountain. This is what we're talking about, right? So you can't you can't really substantiate which interpretation of what you're measuring is true, right? is it 219 because of Earth curve, right? Because of drop over distance, or is it 219 because of some type of curved visual space between you and the mountain peak? How do we mutually verify? How do we verify which one's mutually exclusive, right? And this is where Dr. Heffron basically figured out this concept, right? Well, if I use a star, which will externally tell me, what the angle actually is, he was just as shocked, as we were when we first heard about it. That whoa, the true position of the star matches our tan over rise over run. Like, wait, what?
Right.
Okay, and let's look into this more. And now we're at the point where, like, yeah, and not only is it correct, but if you basically derive any part of the triangle from that occlusion timing, you're actually going to get the right numbers. You're going to get the right distance, the right height. So I don't know where to go from here other than, like, yo, the stars are coplanar with Earth.
And it removes all the variables too, because with optical theodolite, you're going to get different measurements depending on conditions and daily variables. And this removes that completely. And everything that B said, it removes all those variables as well. And occlusion timing is a hard measurement. It's a hard measurement.
I don't think
I
we're
hear
using
you. And one,
coplanar. Go ahead, dude.
I was gonna say one last question because one of them last week said, "Does Stellarium use spherical trigonometry?"
Yes, it's using local hour transformations from the sky to the ground to make latitude and longitude work. It is indeed a spherical coordinate system. Indubitably.
Okay.
Yeah, it's like, here's your oblate spheroid. Apply the information
But
to
again,
it.
remember what I was talking about earlier about how the terrestrial sphere and the celestial sphere are two conceptual models. They have to be used together, and together they're stitched together by relating positions of the stars and where they once were on the first point of Aries, which is where the stars were the night of the vernal equinox. And then they would take zenith measurements of them. And then they just add 15 degrees per hour to that location. So now they have a position of where a star once was, and then 15 degrees per hour, they can figure out where that star is, and that's going to correspond to a position on the ground. That's all Stellarium is referencing. And to make all that work, they have to stitch it together to the center of the terrestrial sphere, which is the geocentric coordinate system transformation that they do, where they compare where the star once was with the first point of Aries to get the 15 degrees per hour, so they can do the local hour transformation to relate the sky angle to the ground. So none of that, like, look, what they want you to believe is, that must mean that the Earth is a globe. All that is math based on a fictitious observer as the reference point. We could do the same thing, and it doesn't, like, the equivalence there doesn't change. None of that. It's not mutually exclusive to a globe. And the thing that makes this so powerful is that the globe, you have to tell it where, you have to enter your coordinates to find out where you're at on it. You can't be like you have to know your time so you can know where that star is at that time, at that angle. You have to give it something. And what we can do is only reference the angle and the elevation of the mountain to get our location. And that supersedes all of their predictions. Like, they can only post-dict that. Like, there is no way that anyone can use this refracted angle that's smaller to get the distance back that comes out of the trig from this that works out for us, because the angle was occluded at an angle that corresponds to a flat Earth where it's higher than what the globe would predict it is. There's no way to get this back. It's geometrically over. There's not a single measurement that they've done that contradicts any of it. We're literally just referencing the time that the star did the occlusion and what the globe predicts, and they're not even close. Or no, I'm sorry, they are close in some scenarios, but the difference isn't the real difference is in the distance, because only one of us is always on. The other one's off by hundreds or thousands of meters, depending on the scenario.
question for you, Alan. I wanted to ask this last time, but the show kind of wrapped up and didn't really get a chance to get a clear explanation. If you were to go with a theodolite from your observing location and actually, go on a full moon night and then, measure the peak that you're using for, the mountain peak that you're using for your occlusion, and you get the altitude and azimuth from the theodolite, and then you go into stellarium and then you look up that particular star that you're going to use that's going to become occluded by that mountain peak, and then you look at the time that stellarium says that star is going to be essentially, at that out azimuth of that mountain peak, which is essentially going to be the moment that it becomes occluded. Are you saying that the time that stellarium will give you for that star to be at that out azimuth is going to be different than what you actually measure?
No, not
Pretending to
no,
misunderstand?
no, not at all. That's a slightly different process than what we're doing here. So you're referencing number one, 219 is the refracted position of the star. The true position of the star at that time for observer location is 204, like 206. So
I don't want to talk about any specific
I know, but just listen. Let me walk you through the whole thing and explain the answer to your question. So if you were to get a theodolite out and measure it optically, right, it would read what the globe predicts during the day. It would be about 219 optically, right? But the time that the true position but simultaneously for an observer on the mountain, the peak of that mountain is at 231, and so is the position of that star. And for an observer X amount of distance away, where we calculated that relative angle for it to be, all of those things are intersected at the same time where the star is no longer visible. So while optically you would measure the apparent position of the star at 219, when you backwards derive your trig off of it, it's wrong. You predict the wrong elevation, you predict the wrong distance. When you use the true position at the peak for your distance that you observed at, you can derive your distance down to the exact meter, and you could closely approximate the actual elevation of the mountain beyond what the globe is able to predict, because they're a much smaller triangle. They're actually never going to be closer. Now, we're never going to be dead on, because, it's the physical reality versus different effects or whatever. So it's always going to be some odd meters off, but the globe is way off in comparison.
Accurate in predicting the time of the occlusion.
Sorry, say that again.
From a totally different
The test
position?
the test that I'm proposing, that we know that this mountain peak, whether you measure it during the day or on a full moon light, the silhouette against the full moon night, and we know that it's at a particular out azimuth, and then we're tracking a star up high, and we look in stellarium to see when the stellarium predict that star will be at the out azimuth of that mountain peak, the instantaneous moment that it's occluded, and stellarium will give you a particular time, and then we go and check to see if that time lines up to what stellarium says. Are you saying that stellarium would be accurate or not be accurate at predicting the occlusion time?
Listen,
I don't even exactly what Ruhiv said.
I don't even know
Just with more words.
what you said, but I laid out the process exactly and explained it. If you need further clarification, I would recommend that you go rewatch what I just said. It's on YouTube.
Yeah. What he said was, if you move the observer back to the Heffron house and you observe an optic angle, would it not be correct? It's completely irrelevant and did exactly what Ruhiv said, but with more words.
Yeah, we're not disputing the optical angle. And if you try to derive your distance and elevation to the peak using that optical angle, it's wrong. That's the purpose of this. When we use the true position with the peak, because at the same time it happens to no longer be visible for us, X distance away, this is the geometric relationship that comes out of that, our distance and closely approximating the elevation of the peak. So what you want to do, moving it to the observer house doesn't help you. Like, we're not disputing the optical angle. In fact, the optical angle, the argument that Jesse was trying to put forward with Mount Blinn, is completely nullified by this analysis. When we derive the predictions based off of the occlusion timing, it's flat Earth every time.
What's the furthest peak from your observation location in your
The
data?
furthest one was 170,000 meters. I think that was
170,000. That's like 100 miles.
I think it's like 87 miles, something like that.
Yeah, something like
was
that.
it Green Mountain? No, it was.
I think it was Green Mountain.
Actually, that's just over 100 miles. But the one you
So,
have on all
so-
these sheets, the biggest one is 10 clicks.
So I'm curious. Then, if you were to take a theodolite and then you measure out the out azimuth of that mountain peak, and
Gonna say it
then you take a theodolite, you measure the altitude. Forget about the azimuth. You just measure the altitude of that mountain peak, right? And you know the elevation that you're at, and you assume that you're on a flat Earth, knowing the elevation of the other mountain peak. Are you saying that if we use trigonometry over a flat Earth, that mountain peak would not show any drop from your observing
No.
location?
Bro, I don't
Because it would be the
even
same
know
as
what you're saying. You're not even talking about the same
No.
thing I'm talking about. I
No,
already
completely different, yeah.
already said that theodolite optical drop isn't in contention. We agree that there's an optical drop. What we're trying to find out is if that drop is physical or if it's optical. Going here, going there with the theodolite, don't care. I agree it's going to be different. There's a drop. Yes. What we're trying to see is that drop physical? If it's physical, then that's going to result in a different time. If it results in a different time, then that time would match what the globe predicts, and it doesn't. It matches what a flat Earth predicts, and when we go to backwards derived distances and elevations based off of that, the globe loses every single time in every scenario at any distance, and we're more accurate. Is there any actual question?
But I guess essentially what I'm saying though,
I'll go to
which
Harry.
is the
No,
part that I just keep getting lost on.
no. Actually, it's not getting lost at all. I completely understand your point. Does anyone else have any questions? I
We
can't
got
go.
this, Alan. It's all right. I'll answer.
I can't do it endlessly.
Feigned ignorance of
Jake,
repetition.
what is your
crazy.
question, bro? What is your actual like? What are you What are you confused about?
From what I can gather is he agrees that if we're to do this observation on a full moon night, where we can see the silhouette of the occlusion mountain, and we're not going to see that star's light, disappear up until we actually see the intersection of that twinkling star. It's going to become occluded the moment that we see it, as it's setting, the moment that it interfaces with that silhouette of the mountain. Right? There's no disagreement there. It's not that the mountains, because essentially what you're saying is that the moment that because I believe your contention is that the moment that the
Jesus
star
fuck.
disappears is the actual position. And so, but you're saying that the mountain in the distance is an apparent position, right? That the silhouette of the mountain, and as far as where it is in altitude and azimuth, is not its true position, but the star, when it disappears, that shows the true position, right? Isn't that the whole point of this whole experiment?
Everything is always apparent. The only thing we're referencing that's fixed would be where the star once was and then adding 15 degrees per hour to that. We're only referencing that. We don't care about what it optically appears. We only care.
You're using the time that
Yes. We're using the time at which the star was occluded, and we're referencing where the true position was at the mountain peak at that time. Yes, that is exactly what we're doing. You got it.
So you're saying that the moment that the star is occluded is the actual position of that mountain peak, correct?
Yes.
What?
Behind it.
That is what it comes out to be. Yes, because there's an optical difference. What you see is optically compressed. Yes.
Hold on. But here's what I'm trying to reconcile, right? You agreed that if we're on a full moon night, and we can see the silhouette of the mountain peak, that star will not become occluded until we actually see the mountain peak and the star touch, and then a moment or so later, that star will become occluded. We agreed there that the star will not become occluded when there's a space between the star and the mountain peak, right?
Hey, Jake, check out in chat real quick.
Yes.
Dr. Mike
Yes or
just
no?
posted Hold on, dude.
I just
Hold
want
on.
an answer to that question. I just want an answer to that question.
Yes.
You asked it like 3 times. And we already answered
And
it.
Yeah.
Check out the
He used
check out the
And I
chat,
think,
bro.
yeah. So,
160 words to say occultation. That was
okay,
crazy.
okay, so then you agree then that that the occultation is not the actual position; it's still an apparent position, right? How could the occultation then be an apparent position, be an actual position? Because you're telling me that the mountain peak is only in an apparent condition, not an actual position. But at the same
That's
time,
irrelevant.
the
That's
occultation.
irrelevant.
Listen,
You're
Jake.
saying that
No.
the
I got you, Jake. I got you. Just listen. Check this out. So, regardless of what you see optically, right? At one point in time, there is a physical occlusion where the star is physically intersecting with the peak, and that's when we no longer see it. Regardless of how we see what angle we see it at optically, in reality, at some point, the light source of that star crossed over that peak, and it's now physically occluded beyond what it can be refracted, and we don't see it. And all we need to know is what time that is. Because when we look at what time that was, we can know what time, or we can reference the true position of the star. And when we do that, it's at the angle of the peak. And so we can draw the implication there that the physical intersection happened at this time, which corresponds to the time that we saw it, but angularly, obviously it's a different angle, but geometrically, based on the occlusion using the true position, we can derive everything about our location and approximate the elevation of the mountain.
But what you're
Yes,
saying
using
is
15 degrees per hour, right?
but
Because
the part
the
that I don't
You
get.
could put a
observation is
spotlight on
movement
that
of
mountain
15
peak and it
degrees
wouldn't
per
make a
hour.
difference. You know, the moon ain't going to do anything. You could put a spotlight. You
Yeah.
can have all your buddies drive up to the top of the mountain and turn their headlights on. It's not going to change the occlusion time.
Yeah, the moon
No,
has nothing to do with
Well,
it. He's just
the
The
part
moon
that
has nothing to do
doesn't
with
make
it.
any sense to me is that you're
Yeah, it's
saying
hypothetical, it's
that
nonsense.
you're saying that the moment that it's occluded, the timing there gives you the true position of the star. The moment that
right.
it's occluded by the mountain gives you the true position of the star. But at the same time, since we both agree that the star is not occluded until it hits the mountain, and you're making the claim that the mountain is at an apparent position, not an actual position, right?
That doesn't matter.
Bro, just
Hold on. Let me explain it
Irrelevant.
real quick.
Yeah, try.
Maybe he'll understand it when the timing is based off of the 15 degree per hour movement of the star. So no matter what angle you're visibly seeing it, you could have high refraction, low refraction, you could have angles on different days, right? You could have different angles based on atmospheric conditions, but based on the timing would give you the distance. Does that make sense? Because you backwards derive it from the timing. So from where you're at, where that star would be at your zenith, when you do 15 degrees per hour and you see where it gets occulted by the mountain, that's where you derive the angles from. Does that make sense? You can't mess with that timing.
I don't see how the apparent position of a mountain, the timing of the apparent position of a mountain, including a star, gives you the actual position of the star. That
So
doesn't.
let me ask you a question. If we did this observation
Wait,
every single day of the week for
wait,
365 days, hold on, let me just finish this real quick. If we did it every single day of the week, 365 days out of the year, and we got the exact same timing for the occultation, but we derived different angles with our theodolite based on atmospheric conditions to where that mountain peak is or where that occultation is taking place, what would be more accurate as to how we would accurately derive the distance between these two things?
Boom.
Or the elevation of the mountain?
Nailed it.
I had a
It would be the
separate
timing that's
question.
consistent every single day, where you have a deviation on how you're measuring it optically every single day. So the more
Before you
accurate
ask
would be the
Anchovy,
timing.
I want a response to that, Jake. What would be more accurate?
I'm just still confused.
Nah, man.
how
What would be more
the apparent
accurate though? Like, let's
position of
try
this
and get
mountain,
unconfused by committing to
how is
answering
it? How is
questions.
it? Well, I don't know how the apparent position of a mountain is giving you the actual position of the star.
So
Because what you're saying, you're saying that
that's our
when we
point
use
entirely.
when
That's
we
our
use the
Jake. That's the entire premise. The refracted mountain can't block the star, so we know when the star is no longer visible, it had to be physically occluded. So we reference where the true position was at that time, and what do you know? It's intersecting with the mountain, with the relative angle to the mountain peak based off of our distance, and we could backwards derive everything off of that time, off of that angle, based off of the occlusion timing, regardless of what it looks like optically. That's why when you go to the observer location and you enter the angle for what the globe, optically sees it at, you don't get the same distance when you backwards derive it. That's the difference between this system here. And
If I may,
if
I think
one's
he's getting.
more, go ahead.
I was just gonna say, I think he's getting tied up in the true position label that we had a problem with last week, where people think you're making the claim of knowing exactly where the star is in real life versus what you're saying with the occlusion timing.
Oh, he's not having that problem at all, but I will go over that real quick. The true position of the star is just the position of where the star once was on the first cusp of Aries. That's what they use for their snapshot and reference point for navigation. And then they just add 15 degrees per hour to that. So where you see a star optically, that's not the true position. The true position, you can think of it as like the star has a light source, but what you see, because it's moving and refraction, it's always going to be a little bit ahead or behind that true position. So that's what we're referencing. So when that position is intersected with the same angle as the mountain peak at that same time, that also matches the time that it wasn't visible when the optical angle would be 219. But when we derive the distances based off of the apparent positions of the mountain, the 219, based off of that, we don't get our distance, and we don't get the actual elevation of the mountain. We're off. When we use the occlusion angle with the same factors, we're spot on for the distance, and we're way closer in the elevation angle. And on top
Do
of
you
that,
agree with
like,
me?
here's the kicker, Jake. Here's the craziest part, right? Like, forget about all that confusion you're having, dude. Why is it when we derive the elevation based off of occlusion timings for the mountain peaks, why is the difference in that always what the globe predicts as globe drop over distance?
I don't know. I haven't looked at that data. I'm
That's a
just trying to
way
understand
that,
the premise of the experiment.
yeah. So that's the premise of it.
Because
And
if we
if,
both agree,
nah, listen, dude. Your
You say the
contribution,
full moon thing again.
yeah,
You say
your
the full moon thing again, I'm done.
no, I'm actually, listen, your contribution here is noted and stuff. Does anyone else have any questions or a different question? And if there's time, we can come back to you, Jake, or something. But like, I'm not gonna, there's nowhere to go from here if you're having trouble understanding it, and we went over it 4 times. I don't think going over it a 5th time is gonna help. Like, so we're gonna have to come back to it. You're gonna have to look into it a little more, like, hit me up in DMs or something, like, at another time, maybe. But like, if you haven't got it yet and you're just saying the same example that I already agreed to, went over you with, told you the distinct differences on, showed you the math differences, like, if you haven't got it yet, then like, the 6th time ain't gonna be the one.
I have a
And
quick
Joby, you
comment.
had another. Oh, sorry. Go ahead, Lily.
Sorry, I have a quick comment. I just wanted to say that, Dr. Heffron's experiment, or whatever you want to call this, is so brilliant. And it's so brilliant in its simplicity that I'm just completely like blown away by how he came up with this idea, this brilliant idea. So I just wanted to make that comment. And also, the other thing I want to say is that my iPad works perfectly and my cell phone works perfectly. Ergo, Earth must be a globe.
God dang it, Lily. How dare you introduce the ultimate argument?
Best reputation
All
since
right.
tonight. All right.
Anyone else have a question? Like, any
Yeah, I
question?
got one.
What's up, Storm?
You guys hiring any bodyguards?
Lily's my bodyguard.
Yeah, they'll have to get through Lily first before they get to us. I'll definitely use her as
Dude,
a
I'm-
shield.
I'm pretty sure
Yep.
Dr. Mike has like 14 attack dogs bigger than humans that he can ride. So I don't know if you want.
All right. Any other questions? Nada, huh?
We-
You guys
we
must just
await
be
your
confounded by this
reciprocal-
information.
All right. So
We'll await your spreadsheets.
quick recap. Here's the spreadsheet for everyone. This is Theo update 13. Here's a link to the spreadsheet. Everyone can get a copy. They can look at the data. They can check everything out. I'll put a link to Mike's spreadsheet in here. So if you want to add more stars or whatever, double check things, you can compare and contrast. But everything in here, like I said, is just plain trig. It's just rise over run or run over rise, depending on how much we're trying to drop the old globe. But then after that, we're just seeing what it is based off of the occlusion angles, and it comes up flat every time. No adjustments, no corrections. Everything in here is steel manning the globe to the maximum possibility. Otherwise, we wouldn't be able to get our distance. We wouldn't be able to derive the elevation to the mountain. There's an adjustable factor here. If you find that the globe is being misrepresented, you can use this terrestrial fraction thing to adjust the geometric globe angle. So you can make it whatever you want, plus or minus, and you can get your maximum representation in there and let me know, how that works out. But yeah, we went over all the measurements here. Distance, always spot on. Globe's off by 11,000 meters over there. Unfortunate. And it's off by 284 on the elevation. Unlucky. And this just goes on and on and on. You can go anywhere, make these measurements. So if anyone would like to participate, right, we need measurements from all over, as our quality assurance, as our head of quality assurance likes to say, bring us more data, please. So what you can do to participate is have the ability to record stars at night and be able to distinguish a mountain peak at night, and just record your latitude and longitude of the peak and where you're observing from. And that's all you have to do. And then just send us that information. Everything else we can look up online to get your elevation at sea level, peak, and all that, distance to peak, etc. Plug everything else in, and the calculator will take care of the time of occlusion or the angle of occlusion, and then everything else will be computated out, and you could participate in this. Any distance, any elevation, don't care.
What'd you say, Daza?
We actually use ECEF to confirm the elevation via Eric. That confirms how wrong your model predicts it to be. Anyway.
Yeah, we had ECEF confirmation. Shout out to Eric, dude. The ECEF master. Yep. Oh, did he just get a new Discord title? The ECEF lad? That's awesome, dude. Shout out to Eric, dude. ECEFing it up for the boys. All right, so if there's any, obviously we'll be back next week to go over this. We've been live for coming up on 2 hours now, so we've hit our quota. We will wrap up, but we're going to be live on the Clubhouse app on Thursday. So if you get a chance to look at the spreadsheet and you want to talk about it over there, you download the Clubhouse app on your respective Android and or iPhone, and then search Flat Earth Gang. Those guys are awesome over there. So we'll be there on Thursday. Tuesday will be Ether Roundtable number 95. We'll be doing a presentation on something. So we'll be doing that on Tuesday. And then, of course, Sunday will be Globebusters. We'll be doing a presentation. Spoiler alert, I'm going to do an update on the Celestial Theodolite and see if we can get more people involved in that and go over this new thing with the data to make it more easy and understandable. So hopefully looking at it like this, it becomes more clear that this isn't about the optics. This isn't about how close the optic angle is. This is about the time of occlusion and what triangles we can derive from that best represent the geometry of the Earth. and it doesn't go out. It doesn't go well for the globe. All right. Thanks, everyone. We'll see you guys tomorrow. I'll be right back. I'll roll the intro credits, outros. All right, everyone. Thanks for hanging out. Shout out to the YouTube chat. I see the lads in there holding it down. My boy Archangel, Scott Snowden, Shalom Shire, Brian Cash, Carbonated Lifeform, Bredimus, the homie. Shout out to Bredimus. Free Thinking. We got Run Boston Bear, Big Pine, Bill Hickok, and Brian Cash again. And Glinda, shout out to Glinda, Tony Coriolis. All right, I think that's everyone. We'll see you guys tomorrow. Peace.